Hello everyone, welcome back to the next video on game theory. So far, what we have seen in game theory is we had solved certain problems which involved both pure and mixed strategies. Of course, pure strategy was straightforward, simple, but when it came to mixed strategy, we discussed different methodology to solve, out of which one was algebraic method and the second one was with arithmetic method. Both these methods actually are used to solve game theory problems which involves mixed strategy. Apart from that, we also have seen one of the most important feature of game theory, that is called as principle of dominance, where any large matrix was able to reduce to 2 cross 2 by using or by implementing various principles of dominance. The dominance was in with respect to rows and with respect to columns as well. And once we reduce any large matrix, any large payoff matrix with the principles of dominance, then we implemented arithmetic and algebraic method to get the strategies used by different players, and then we found the value of the game. Now, in this particular video, we are going to look at the last aspect of game theory, and that is nothing but graphical approach. Now, couple of points before we proceed and try to understand how we basically land up trying to solve the problems related to game theory using graphical approach. The first one is this method is applicable to only those games in which one of the players has two strategies, right? So you cannot have a matrix which is n cross n where n is greater than 2. Right? So one of the player should have only two strategies, in which case we can implement graphical approach. What is the advantage? The advantage of this method is that it is relatively fast and it reduces 2 cross n or m cross 2 game to 2 cross 2 by identifying and eliminating the dominated strategies, and then the game can be solved by mixed strategy method. Now, when I say mixed strategy, we'll end up again using our old method, either arithmetic or algebraic method. And very interesting is this particular method is interesting as it explains the idea of saddle point graphically. Now let us try to understand how to solve this problem using graphical method. So I have a problem in front of you, and what it says is the problem statement is consider the payoff matrix of player A as shown in the table and solve it optimally using graphical method. So you have player A with the two strategies, A1 and A2, and you have player B with 5 strategies, right? Now just see, out of these two players, the one player, player A, is having two strategies, right? So it is 2 cross 5. The order of the matrix is 2 cross 5, and that's what I said you earlier, that this particular approach is used only when one of the player has two strategies, right? And the number of columns is 5, so this is actually called as 2 cross n game, right? 2 cross n game where n can have any value, right? That is player B strategy. So I have both the players with these strategies, and let me explain you how do we solve this graphically. So look at the solution. This is a 2 cross n game, as I have already told you. Now this particular game do not have a saddle point, right? So what we do is we implement the principles of dominance to reduce it to 2 cross 2, and then I can take it up further. But sometimes what happens, it may not be reduced to 2 cross 2 also. So when it doesn't gets reduced to 2 cross 2, let us see how best we can solve this problem. So while implementing the principle of dominance, I realized that column 5 is dominated by column 1, and at the same time, right, column 2 is dominated by column 4, right? So in the previous video, we have seen principle of dominance. So I'm not going to go into a deeper aspect of it, just understand. And then because of this dominance principle, I'm going to remove B2 and B5. So I'm going to remove this particular column, that particular strategy, and this particular strategy or this particular column. So once I remove B2 and B5, this is how I get my matrix. Okay, So once I get this particular matrix, I have 2 strategies for A and 3 strategies for B. Now when you look at closely this particular matrix or this particular payoff matrix, I draw conclusion that this matrix cannot be reduced further. Understand? This matrix cannot be reduced further. And you very well know that if the payoff matrix is not 2 cross 2, then I cannot implement algebraic method or arithmetic method. And that is where the graphical method or the graphical approach plays a very, very important and vital role. So once I draw conclusion that I cannot reduce the matrix, what I do is I draw the graph for the reduced payoff matrix, right? So I draw the graph for the reduced payoff matrix. Now I already drawn the graph and I'll show you how to basically go about it. So what you have to do is you have to basically have 2 axes, one for player A, right, and the lines for player B. So just have a look at it. Okay, so I have 2 vertical lines. This particular vertical line on the left hand side is for A2 strategy, which is adopted by player A, and the right hand side vertical line, this is for player A but for A1 strategy, right? So the left hand side line is for A2 and the right hand side is for A1. There's no hard bound rule. You can still swap it and do it. It all depends upon, absolutely no worry. Now actually you have to draw this this particular approach using graph sheets, right? You have to kindly excuse me, I was running away of the graph sheets, so I just drawn on a piece of paper, I have scanned it and I'm uploading it here. So let us see how do we draw the lines, right? Left side is A2 and the right side is A1. Now look at your reduced matrix. I have this for B1 strategy, I have value of A1 as 3 and I have value of A2 as minus 1, right? So I have 3 and minus 1 for B1 strategy. So what I do is I draw the line from, this is my A2, right? This is A2. So from minus 1, I will draw the line to 3. This is 1, which comes and sits here. So I'll draw the line which connects minus 1 of A2 to 3 of A1. So this line belongs to B1. You can see here, this particular line belongs to B1. So that is what it is. Then I'll draw a line from 6 to minus 2, right, which belongs to B3. So this is my minus 2 of A2 strategy. From here, the line goes up to here, and this is my 6 of line of A1 strategy. So this line from minus 2 to 6, it belongs to B3 strategy. Similarly, I draw the line from minus 1 to 2, right? Minus 1 to 2. So minus 1 is my A1 strategy and 2 is my A2 strategy. So the line is drawn from minus 1 to 2. So this belongs to B4 strategy. So all these 3 lines have been drawn on the graph, right? So which belongs to B1, B3 and B4 strategies, right? Now since we are talking about A as a maximin type player, okay? Since it is a 2 cross n game, right? Understand? Since it is a 2 cross n game, we always consider A as a maximin player, right? And what we do? We identify the highest intersection point in the lower boundary of the graph. Understand? Right? Since A is maximin type player, we identify the highest intersection point in the lower boundary of the graph. So this is my lower boundary. Whatever I have shaded, which will touch all the lines below, right? That is called as lower boundary. Now in this particular lower boundary, you can see this, right? This is my lower boundary. So in this particular lower boundary, this is my highest intersection point, this one, right? So that is my highest intersection point, which I have actually called as point C, right? So this is my point C. Now this point C is the highest intersection point which is associated with 2 lines, right? That is this line, okay, this line and this line. So this highest intersection point is associated with these 2 lines, and these 2 lines belongs to 2 strategies, which is nothing but B1 and B4. Okay, I repeat, since player A is maxim in type, we identify the highest intersection point in the lower boundary, right? So this is the lower boundary which will cover all the lines that you have drawn in this graph. That is the three strategies of player B. Now in this particular shaded region, you are going to identify the highest intersection point, which is this. When you closely observe, this intersection point belongs to two lines, that is, it belongs to two strategies, B1 and B4, right? So that's what I made a statement. Point C is the highest intersection point which is associated with B1 and B4 strategy, right? So what you do after identifying the strategy, this is what is your matrix actually speaking, right? Now, once you identify the two strategies for which you have got the highest intersection point, you remove the strategy which is left out. Now, since our strategy was B1 and B4 which was identified, right, excluding those two strategies, I am going to remove the third strategy, which is nothing but B3. And once I remove B3, I will get this particular payoff matrix, which leaves me only B1 and B4 strategy for player B. So that's what I have said. The payoff matrix now gets reduced to this particular matrix, right? Now, there's nothing great over this, which we have to do it afterwards, right? Since we are already aware, this is class 2 payoff matrix. So what you do? We implement arithmetic method to solve the game, which we have already done earlier, right? So this is the arithmetic method, right, which we have already done earlier and solved a couple of problems. So I'm not going to focus on that. Now, once I do this, I come out with a conclusion that A uses a strategy which is 3 by 7 and 4 by 7, and B uses mixed strategy 3 by 7 and 4 by 7, right? But when you finally write the solution in terms of the strategies used by player A and player B, you have to be a little bit careful, because the original payoff matrix is not 2 cross 2, correct? The original payoff matrix which was given to you is 2 cross 5, and hence the solution that you write should represent the values for two strategies of player A and 5 strategies of player B. I repeat, the strategies that you write as the answer, as the final answer, right? You have to mention 2 strategies for player A and 5 strategies for player B. So, of course, there's no doubt about 2 strategies used by player A. So I just land up writing 3 by 7 and 4 by 7. But then here we made a statement that player B uses mixed strategy of 3 by 7 and 4 by 7. But this 3 by 7 and 4 by 7 belongs to B1 and B4. That means player B uses mixed strategy, that is B1 and B4, right? But player B has got originally 5 strategies in the payoff matrix. So what you do is you write this 3 by 7 for B1, you write this 4 by 7 for B4, and the strategies that player B is not using here is B2, B3 and B5. And hence what you do is for those 3 strategies, B2, B3 and B5, you mention it as 0, right? So this particular line tells me that B uses strategy B1, which is in red color, that is 3 by 7, and strategy B4, which is again I have highlighted in red color, which is 4 by 7. Now when I look at the reduced matrix, I get the values of my A11 and all like this, right? So the value of the game, I don't need to explain you once again. I'll just substitute in this particular formula, which we have already seen in the previous videos, right? Once I substitute the values of all these A11 up to A22, I get the value of the game as 5 by 7, right? So the value of this particular game is 5 by 7. So that's how you'll end up solving a problem which involves 2 cross n matrix graphically. Let us make things more clear and much better. Let us try to solve one more problem which involves 2 cross n. So you have a look at this. So this is my 2 cross n. Again, no saddle point. Now, the best part in this particular problem is no course of action dominates the other, and hence the matrix cannot be further reduced. So don't be under impression that whenever you are given a problem to solve graphically, I can always use principle of dominance and reduce it, and then I'll get the reduced matrix. Not necessarily, right? If your luck is good, you may get like that. But this particular example, I'm unable to implement the principle of dominance to reduce the matrix. No, neither the row nor the column is dominating the other row or column respectively. Hence, the matrix cannot be further reduced. Now, what happens when matrix cannot be further reduced? It's very simple. You have to draw all the 5 lines for the 5 strategies that are adopted by player B. It's as simple as, right? So I have to draw a line from -5 to 8. Then I have to draw a line from 5 to -4. Similarly, all the remaining 3 lines and the last line from 8 to -5. So when I closely observe and draw the lines for all the strategies of player B and 2 strategies of player A, this is the graph that I get, right? And this is what is my, now this particular portion where you get no small dotted lines, below portion is the shaded portion actually, and the highest intersection point is here, this one, highest intersection point, where I've written maximum point with the arrow. So the highest intersection point is associated with B1 and B3 strategy, and hence the payoff matrix gets reduced to -5, 0, 8, -1. So this is B1 and B3 strategy with respect to your original payoff matrix. So this is B1 and this is B3. So -5, 0, 8, -1. Okay, so that is the payoff matrix. And as usual, we implement the arithmetic method to solve the game. So this is the strategy used by player A, 9 by 14 and 5 by 14. And player B uses strategy 1 by 14 for B1 and 13 by 14 for B3. So you have to be extremely careful when you write the strategies for player B here, right? So you just cannot write the way you have written for player A. It's very for simple reason, player B in the original payoff matrix, he has been given 5 strategies, and hence the optimal strategy used by player B should also reflect the 5 strategies. Since he is using a mixed strategy which involves B1 and B3, all other strategies except B1 and B3 becomes 0. See here, this is my B2, this is my B4 and B5. And hence, I draw conclusion that player B uses strategy 1 by 14, 0, 13 by 14, 0 and 0. And I have my values of A11 up to A22 like this. I just substitute these values in the formula, which you are already aware, and I get the value of the game as -5 by 14. So this is how basically you will end up solving the graphical problems which involves 2 cross n game. Now let us look into the last aspect of it, right? I'll just cover in one video because not much explanation is required. The next type of problem statement in graphical approach is m cross 2. That's what we have seen in the original introduction, that 2 cross n or m cross 2. So when you say 2 cross n, player B has got more strategies, and when you say m cross 2, player A has got more strategies. So let us look at that particular type of problem. So I have here, consider the payoff matrix of player A and solve it optimally. So I have 4 strategies for player A and 2 strategies for player B. So this is called as m cross 2 game. So be careful. This is called as m cross 2 game, right? Except one point, and that point is in terms of identifying the shaded region and the intersection point, rest procedure remains same, right? So m cross 2 procedure is by and large same as 2 cross n. So here I observe there's no saddle point, no course of action dominates the other, hence matrix cannot be reduced. So I'll end up drawing lines for all the strategies, right? So I have this player A1 strategy as 1 and 3. So here what I do is I have this vertical lines. In the earlier case, the vertical lines were belonging to player A, but here the vertical lines will belong to player B. So on the left hand side vertical line I have used for B2, and on the right hand side I have used for B1. Now the strategy adopted by A1 is 1 to 3, right? So B1 is 1 and B2 is 3. So this is my B1, this is my 1, and I have this line drawn from here to here. So this is my 3. So I've drawn a line from 1 to 3. This is for A1 strategy. Similarly, let me take one more for A2. This is from B1 is 3 and B2 is 1. Okay, B2 is 1 and B1 is 3. So this is my 3 B1. From here the line comes to B2. This is my 1. So this particular line is for A2 strategy. So similarly what I do is I draw lines for all the 4 strategies A1 to A4, which is reflected on the graph sheet. Now since it is M cross 2, we say player B is minimax type. Okay, player B is minimax type, and what we do is we identify the lowest intersection point in the upper boundary of the graph. Okay, so be careful here. Since it is M cross 2 game, we have player B as a minimax type player, and we identify the lowest intersection point in the upper boundary of the graph. Now this is your upper boundary where I have shaded, right, which lies above all the strategy lines that you have drawn. So that is the difference, right? In the earlier case, 2 cross n, we identified the highest intersection point in the lower boundary, whereas in this case, which is M cross 2, we identify the lowest intersection point in the upper boundary. And then once I identify the lowest intersection point, which is here, I draw conclusion that point B is at the lowest intersection point, and which is associated with A1 and A3 strategy, right? So the lowest intersection point in this example is with respect to A1 and A3 strategy. So as usual, what I do is I will retain my A1 and A3 strategy, and I will delete all other strategies. So here I will delete A2 and A4, and hence my reduced payoff matrix looks like this. So I have A1 and A3, and as usual I have B1 and B2 for player B. So my payoff matrix gets reduced like this, and then I implement my arithmetic method to solve the game. Okay, now again coming back to the strategies used by player A, I get 3 by 4 and 1 by 4, but 3 by 4 and 1 by 4 is for A1 and A3. Okay, it is for A1 and A3. So I will use 3 by 4 for A1. A2 is 0 because player A is not using that strategy. A3 is 1 by 4, and again since he is not using A4 strategy, it will be mentioned as 0. So the strategies used by player A is 3 by 4, 0, 1 by 4, 0, while player B is 1 by 2 and 1 by 2. And with the information that I have got with the payoff matrix, this is what the values I have, and I substitute these values to find out the value of the game, which is nothing but 2 in this case. Let us also see one more problem of M cross 2 before I wind out this particular module. So consider the payoff matrix, right? So this is what it is. I have 4 strategies for player A, 2 strategies for player B, no saddle point, no course of action dominates. So I'm not going to implement the principle of dominance. I'm going to land up drawing lines for all the strategies. So my graph looks like this. Sorry for the clarity. So once I draw this is my lowest intersection point in the upper region, which actually belongs to A1 and A4, right? And hence my payoff matrix gets reduced to this, and then I implement the arithmetic method to solve the problem. So this is my strategy which I get finally. Player A uses 13 by 15, 0, 0, 2 by 15, while player B uses 11 by 15 and 4 by 15. These are the values which I get from my reduced payoff matrix, and then I substitute as usual, and I'll get the value of this particular game as 68 by 15. So that basically ends the game theory module, right? Please feel free to get back to me for any sort of clarifications. But the only request is, as I have been telling you guys earlier, that the field of operation research, you cannot become master of it unless you solve more and more and more number of problems. There's no end to solve the problems, right? So I have limitations. I can only solve one or two problems or maybe one more, but then irrespective of the number of problems I solve, correct, unless you take paper and pencil and you do not solve the problem, right, you will never become you will never become, or you'll never have a mastery on this particular subject, right? So my sincere request is, just pick up paper and pencil and keep solving as many problems as possible. Okay, thank you.